So let us take few more questions in data structure and algorithm. What do you mean by complexity of an algorithm? Complexity. Explain the meaning of worst case analysis, best case analysis with an example. We'll talk about the average case also. So complexity, what does it mean? How complex is your algorithm with respect to or in terms of your time it takes to run or the space it will require while running. So this is like this. The complexity of an algorithm, say M, it is the function Fn which gives the running time and the storage space requirement of an algorithm in terms of the size n of the input data. So what exactly we are trying to do here is, for an input, n can be say 10, and can be some 10 to the power 20. So these values, these input data, depending upon this data, how this algorithm works, how this algorithm grows with respect to the time and space. So the storage space required by an algorithm is simply by a multiplication of data size n. Not exactly this, but by algorithm also we compute the space complexity, and this complexity refers to the running time of the algorithm. It is the running time of the algorithm. So for a function fn, there are certain cases. The important is the worst case and the best case. The average case is somewhere in between. So the two cases we investigate for complexity. Worst case is the maximum number of fn for any possible input, and the best case is the minimum possible value of fn function. For example, because the example is also asked to be taken. So if we take a example of linear search in which an integer item is searched in a array data, we call it as a array data. So the complexity if the search algorithm is given by the number c of the comparison between the item and the data. That means how many times you search or compare each item to find the value. The worst case would be when the item is at the last or is not there at all. In both the cases, the complexity would be order of n. So this is big O of n. Why we call it as big O of n? Because this is the asymptotic notation for the function which is governing or which is always higher than this fn. The average case, we assume that the item is present in the array and is likely to be present in any position in the array. So the best case would be you find the item at the first position. The worst case would be at the nth position. So n plus 1 by 2. Okay, this is how we can tell. But there is another way also, that the item may be present at any position. So the number of comparison that needs to be carried out for these numbers 1, 2, 3. Say these are n. So each number occurs with the probability 1 by n. So how many are there? 1 into 1 by n plus 2 into 1 by n, that is n plus 1 by 2. So the average number of comparison needed to locate the item in the array, which is we have taken as a data, is approximately equal to the half the number of elements in the data list. Explain the method to calculate the address of an element in an array. First of all, a 25 into 4 matrix array data is stored in a memory in a row major order. Row major order, if the base address is 200 and w, that is the words per memory cycle, is 4 cell. Calculate the data 12.3, the address of data 12.3. So what exactly is your row major? Let me tell you row major and column major. So if this is a matrix and we have number of rows, number of columns, so the first row will be placed in the memory, then the second one, then this third row. This is the row major. So we need to know the method to calculate the address of an element in an array. First of all, we have a 25 by 4 matrix array which is in row major order. So if the base address is 200 and we have to find the address of 12.3. So how we are going to do it? As we have already discussed in the previous questions, that the row major representation, the address of any element aij, can be found using the following. Like aij would be base a, and what would be base a? That will be 200 plus I into m plus j. What is this m? M is the this words per memory cell. I is ij, that is will place this 12 and 3 here, and into size. Into size, this is 4. And let me change what I said. This m is not the size, but it is the, if these are the rows, these are the columns. So the column width. So it is 4 here. 25 into 4, so this will be m equal to 4. And this question, these two are similar, that is 4 and 4, so we'll write 4 and 4 here, but m will correspond to the second part of the matrix, that is the column, because actually we have to compute the columns only. These are 1 2 3 4 say column, so 4 column. Then again we have to run for 4, so 4 4 4, this like first it will be 4, then 8, then it will be 12, like this. For every point or every element we have to start with 0 or say 1, and then we go to 4, then we go to 8, like this. That is why we have m here. So now this is a formula for us. We can directly input the values, or we can place the values and find out that the address is 404. What is the difference between grounded header linked list and a circular header linked list? Header linked list is a linked list which always contains a special node, which is called the header node at the beginning of the list. So we have two kinds of header linked lists, which are grounded header linked list and circular header linked list. And the difference is of these two, grounded and circular, is that the grounded header list, this is a header list where the last node contains the null pointer. And in the circular header list, the header list where the last node points back to the header node. Okay, whenever we have a linked list, every node has the information of the next node. How? Because the second part, along with the data, the second part will contain the address of the next one. But our situation is, if this is null, then how to know where this link is starting? So we need to have a header node which is pointing to the first node. So header contains the address from where this linked list is starting, and we know that this linked list is logically distributed. It is not contiguous memory like array. So this is header, and what this grounded header means, why I showed it grounded. Grounded means in electricity we show ground by this symbol. So if it is null, the link or the last node contains the null pointer. If it is null, this is a grounded header list. While if apart from, or rather than having null here, it contains the address of the header, that is the first node, this will be known as a circular header list. Write an algorithm to insert a node in the beginning of the linked list. So now we have just seen the linked list, how to insert a header. See, if this is a linked list, the number of nodes here. So a header will be pointing to this node. So if we want to point, or we want to insert an element here or a node here, we want this header to be pointing to this node, and the next stop, that means the address part of the inserting node should point to the first node. So this is the requirement, and this is how we are going to make the algorithm. So this is a structure we are using, which is structure node, and the link, which is this link, is of type structure node only. So how to add at beginning? We have structure node, and this is double pointer. That means we'll take a temporary node, we'll assign a size. First we are going to create a node. We have to create this node also. So we are creating a node using temp. The number will be, or the value, this number, data or number, will be given to the data part, this data part, and the link will be this one. The link will be the pointer q, and the temp will be pointing to q. So this temp will be pointing to q. This is how, and this q, that is the next link, will be pointing to, this will be pointing to this, and the actual will be pointed by the new header. So this is how we are going to insert a node. Write an algorithm which does depth first search through an unweighted connected graph. In an unweighted graph, would breadth first search or depth first search or neither find a shortest path tree from some node? Why? Write an algorithm which does depth first search. So this is an algorithm for depth first search through an unweighted connected graph, and this is self-explanatory, and we have implemented it through this list. So I hope you'll be able to understand it. I leave it here. Now we have to convert the infix expression, these following infix expression, into its equivalent postfix form. So how we are going to convert it? First, let us take this one, first one, and we know that the first preference goes to the brackets. So we'll perform this first and this one. And in this we have plus and the cap. That is, if we consider it to be an exponent. So let us see. First we will do this BD cap. So this will be BD cap. And still not we have done, we have completely done this bracket. So we have A, this is the first operand, BD is the second operand, BD star is the second operand, and plus is the operator. So A with BD star and then plus will be here, because we have to write the postfix. So this plus will be in the last. Okay, this is done. Now let us see EF. EF, because these two are operand and minus, so operator will come here, this operator, EF will be like this. Now these two are done, and we have to find between this division and plus. We know that division is the first one. So first operand is this, second operand is this, and the operator is this. So first one, second one, and then the operator. This is again in the bracket, but we have plus here, so it doesn't matter. We'll take first operand is this one, second is this one, and third is plus. So we'll take this G and then plus. So this is the postfix expression. I hope you'll be able to do this also in the similar fashion. What is quicksort? Sort the following array using quicksort method. So in this quicksort, what we do, we have an important aspect here of partitioning. We can do it recursively through partitioning, and this quicksort uses a pivot element. First, a pivot element has to be seen, and then this pivot element is checked, and once this partition is made, this pivot element will find its place with the left one or the right one already sorted. So let us see how we can do it. So quicksort gives a very good running time of n log n, which is comparable to the merge sort. So that is why quicksort is also a classic example when it is taught to the computer science students. So quicksort is a sorting algorithm that uses the idea of divide and conquer, similar to the merge sort. So this algorithm chooses an element known as a pivot element and finds its position in the array such that it partitions the array into two subarrays. The elements of the left subarray, they are always less than the pivot element, and the element in the right subarray are all greater than the dividing element, that is the pivot element we are talking about. So let us see with an example the algorithm which is repeated separately for these two subarrays. So we have these numbers 25, 56, 47, 37, 10, 90, 82, 31. So this is first one, pass one. So what pivot element you can take? This pivot element will be always, this is a custom that we take pivot element as this. So first we see that when we are comparing, but this is what we do. We also start take 2 pointers in the actual algorithm. So the shifting is done, or the swapping is done, and then the comparison. But we'll try to just give you a hint or an exemplification of how it is done. See, first the element here, we see that in this the 10 element or 10 is the best position of 10 is here. So we insert 10 here, and all other elements we shift. So this is 24. We take 24 as the pivot element. So all the element, why we are taking it as a element pivot, that is to partition, that is because all the element on the left side is less than 24. All the elements on the right side is greater than. So this is fine because all the elements are less. So now we are left with this part. So we need to apply this again. Same theory to this partition also. Here also we see that this element which is 56, which is to be sent here, and 90 to be sent here, and 31 to be replaced to correct position. 56. If we take 56 as the element after some certain algorithm is quite complex. So I'm just showing you, just giving you an idea. Don't compare with the actual, because the actual algorithm is quite complex. This is first partition, this is second partition, and now we recursively apply this, the application on this, and the same on this. In this we see that we are left with one element, and these two are sorted. Again, these two are when we compare this, we have to compare this, means we have to shift 82 here and 90 here. So what I am trying to say is, when we do certain partition with certain pivot element at every point, we see that the final phase we have the sorted element. So I'm not saying that this is the actual example I have given with all the arrays and the the values which are partitioned. What I'm trying to say is, this is just a way in which we do, and I'm just trying to show the partitions we make with the pivot element. How many key comparisons and assignments an insertion sort make in its worst case? See, the worst case performance in an insertion sort. Insertion sort is what? Insertion sort is if you have one card, okay, in your hand. So you pick a second card from your right hand and place it in the right position in the left hand. Then you again pick a card and you compare it with the first two and place it in the correct position. So the worst case is, in the insertion sort, occurs when the element of the input array are in descending order. That means you have to compare, if you have one card and second card you choose from the pile, you have to compare it with the one card. Now you have two cards in your left hand. You take one more card. Now you are comparing it with two, not one but with two, and you're placing it, so it will be two comparison. Now you have three cards. Now you are taking one more card and you are comparing it with three cards, so there will be three comparison because it is a descending. The order is descending order, so you have to compare with first one time, two times, three times, like this. So in the first case, the first pass requires one comparison, then two comparison, then three comparison. Likewise, for the kth pass, it will be k minus 1 comparison. And finally, it will be n minus 1 comparison, because to make it full, say 52, the 52nd card will be compared with all the 51 cards because the order is descending already. So the total number of comparison will be 1 plus 2 till n minus 1. So that will be n minus 1 by 2, that is out of n square. Create a heap with the following list of keys. You know, in heap what happens? If it is a max heap, the highest element is here. So all the elements on the left or right subtree will always be less than this. And this will be recursive. That means all the elements here will always be greater than these left or right subchild. So a heap is like this. We can make a heap 8. So this is the heap actually. The answer is this only. And you can just verify that all the elements, the highest element is 22. In the left, highest element is 20 if it is compared with all the nodes here. So this is how we make a heap. The actual heap making is, it will take some time. So just see how we can make it or how the formation would be. Now these are the values that are stored in a hash table. So you have a hash table, these values are stored. You need to describe how the values are hashed by using division method of hashing with a table size of 7. So you have a table size of 7, you have to use this division method. Use chaining as the method of collision resolution. So you have to use the chaining method also for collision resolution. So what is the table size? It is 7. So where 25 will go, and you have to use the division method. So that will be modulo actually. Not division, but it is a modulo method. So what we are going to find is, we'll take all the values and modulo it with 7 because the table size is 7. So 25 modulo 7, then all these like 197 modulo 7. So these will be 4053411. So these are the values now. And how you are going to resolve the collision? These are seven say boxes, or you can say a table. So you can place 0, 1, 2, 3, 4, 5, 6. So where this 4 is going to, this 25 is going to lie. 25 has a hash key generation of the value 4. So this bucket will contain 25. Also we have 102 also, so it will be 102 and then null. How we are going to place say in the bucket 2, is there any value with 2? No, so we'll place null. So we'll make a link. This is the chaining. So we have made a chain because when 25 will come, when it will be placed in 4, but when 102 will come, what will be the problem? Because this is already contained. So 4 is assigned for 25. So what about 102? So we'll make a chain. So we have made a chain, a linked list type of structure, and finally we'll make it as null. So this is how we make a hash using division method. Write a non-recursive algorithm to traverse a binary tree in order. You have to write a recursive relationship or algorithm. So how to write, the non-recursive algorithm. So non-recursive algorithm to traverse a binary tree would be something like this. Initially we push null onto the stack, null, and then we set PTR to root. So this is a root, pointer to root. Then we repeat these step until null is popped from the stack. So we proceed down to the leftmost, rooted at PTR, pushing each node n onto the stack here, and stopping when the node n with no left child is pushed onto the stack. So all the left one will be pushed, and if there is no anyone to be pushed, we stop. Then we start popping and processing the node on the stack. So if we come to null, that is null is popped, then we exit. If the node n with a right child is processed, we set PTR to the right, this pointer to the right one. By assigning this PTR is equal to right of PTR. And we return to step the first one. This again we start with this. Means this is a non-recursive, so we repeat it until we find the null. Describe the insertion sort with proper algorithm. What is the complexity of insertion sort in the worst case? So this is the insertion algorithm or insertion sort. So one of the simplest sorting algorithm is insertion sort. As I explained with the cards, the insertion sort consists of n-1 passes. n-1 passes. We start with pass 2 because in the list of elements we start with, this is already sorted, one element is already sorted. So we start with this 2 through n, and we insert sort or insertion sort ensures that the element in the position 1 through the p they are sorted. So insertion sort makes use of the fact that those elements in the position 1 through p-1 they are already known to be in sorted order. Okay. So this is insertion sort if this is say some array and this is a number and we have certain local variables with temp also. We start with A0 and assign it as minimum data, that is a sentinel. We start with 2 till n, and for every value we start from p, that is the p, and we go up to aj-1 and we exchange aj with aj-1, and then we, after this exchanging, we again see that we have reached to the last or not. So every time the p will come or the position p will come, we assign it to temp and we move temp to aj-1 till the point we reach the end. So because of the nested loops, each of which can take n iterations, insertion sort will be, because this is for and this is again for, and they both use this p, that is n, they both use n. So n into n, that will be n square. So furthermore this bound is tight because input in reverse order can actually achieve this bound. A precise calculation shows that the test at line 4 can be executed at most p times, and for each value of p, so summing over all this p, that will be n-1/2, that is order of n square. What are the two standard ways of traversing a graph? Explain them with an example of each. So there are two ways, we have been discussing it a lot, depth first traversal and breadth first traversal. So in depth first traversal of a graph, it is like the depth first traversal of a tree. Breadth first of a graph is like breadth first traversal of a tree. Since a graph has no root, when do a depth first traversal? So when we do this depth first traversal, we must specify the vertex at which to begin. Not a root, but any vertex. So depth first traversal of a graph visits a vertex and recursively visits all the vertices adjacent to that node, which is adjacent. This is adjacent, this is adjacent. So this the catch is that the graph may contain cycles, but the traversal must visit every vertex at most once, only once. So it may contain cycles. The solution to the problem is to keep track of the nodes that have been visited. So if this has been visited, we will not visit again. We will go to the next one. So the traversal node, traversal does not suffer the fate of infinite recursion because we have this keeping track of the previous nodes. In the breadth first traversal, it is just like a graph, like a breadth first traversal of a tree. So breadth BFS, BFT, first visits all the nodes at depth 0, that is the root. Then all the nodes at the depth 1. Let me just give you a glimpse. In this breadth first, we traversed this, then this, then these, all these. So all the nodes at the depth, and since the graph has no root, then we do a breadth first traversal. We must specify a vertex again at which to start the traversal. So we can define the depth of a given vertex to be the length of the shortest path from the starting vertex to the given vertex. This is the depth here. So breadth first traversal first visit the starting vertex, then all the adjacent vertex to the starting vertex, and all the vertices adjacent to those. So first we go to all the node which is adjacent, then we go to this which are all adjacent like this. So all the vertices which are adjacent to the starting vertex, then all the vertices adjacent to those, and so on and so forth. This is breadth first traversal. Consider this graph G where the vertex are 1, 2, 3, 4 and these are the edges. We need to draw undirected graph and its adjacency matrix. So the undirected graph and adjacency matrix would be like this. These are the vertex, these are the undirected graph. We'll start with 1, 2, then 1, 3, and 3, 3 also has. Then we have 3, 4, then 4, 1. Okay, this will be or undirected graph, and the adjacency list would be something like this, because we have to make these are 4 nodes of 4 row 4 columns, so that there will be 16 entries. And since this 1 2, that is, we can directly write 1 2, so we'll write 1 here, 1 3, that will be this 1 and 3, and then we have 3 3, so 3 3 also will be get populated by 1. Then we have 3 4, so 1, and then 4 1, that is, this is 4 and this is 1. So these are the values, and since we have 4 1 also, that will be this one. So in all we have 1 2 3 4 5, so 1 2 3 4 5 ones. Okay. Write short notes or explain B tree, abstract data type, and simulation of queues. So B tree, we'll start with B tree. Just like your AVL tree, is it a balanced tree? Just like AVL tree, these are balanced binary search tree, so you will not get any tree like this, which is again a binary tree, but it is not balanced. So B trees are balanced M-way search tree, like AVL balanced tree. B tree are M-way, so you will not have only one value in the node. You will not have one value in the node. You will have more than one value in the node. You can have more than one keys, or not one but M keys. So this is an M-way search key. By imposing a balance condition, the shape of the AVL is constrained in a way which guarantees the search, insertion, and withdrawal operations, or they are all of order of log n. Order of log n, so where n is the number of items in the tree. The shapes of B tree are constrained for the same reason with the same effect like AVL. So B tree of order m is either the empty tree or it is a M-way search tree with certain properties. The properties are like this. The root of T has at least 2 subtrees and at most m subtrees. So have at least means this will have at least two subtrees, or if this is M-way tree, it can have, say m is 3, so it can have 3 subtrees. All internal nodes of T, which is other than this root, have between m by 2 and m elements. So 3 by 3, so it will have 3 by 2 to 3 element. Okay, so it will be between 1 and 3. 3 by 2 is 1 only. So it will be 1 and 3. So it can have 1, 2 or 3. So the internal nodes of tree can have 1 or 3, 1, 2 or 3 subtrees. And all external nodes of T are at the same level. So all the external nodes, means the last one, the leaf we are talking about, they are at the same level. What is abstract data types? Now this is a very, sometimes this is a favorite questions of the interviewer, because data type you know about, you cannot speak about stack, queues, and etc. But what about abstract data types? This is always asked, because this shows that you know the data structure well. A useful tool for specifying the logical properties of data type is the abstract data type. The term abstract data type refers to the basic mathematical concept that defines the data type. It is defining the data type, the mathematical concept which is defining the data type. So in defining ADT, abstract data type, as a mathematical concept, we are concerned with the space and time efficiency. And ADT consists of 2 parts, the value definition and the operator definition. So it has value definition also and operator definition also. So value definition defines the collection of values for the ADT and consists of 2 parts, the definition and condition clause. For example, the value consists definition for the ADT rational states that a rational value contains 2 integers, the second of which does not equal to 0. So we use array notation to indicate the parts of an abstract data type. And let me tell you one more thing about ADT. ADT is basically about, it is a closed, it is an abstraction level. So what it talks about the operation which can be applied on the data type or the data structure, right? It talks about the data, it talks about the application on the data, but it doesn't talk about the implementation. It is up to you how you implement it, but it will tell you that it has to be efficient. The data should be these, and the operations on it will be like this. This is abstract data types. Now we'll come to the next one, that is the simulation of queues. So simulation is the process of forming an abstract model of a real world situation in order to understand the effect of modification and the effect of introducing various strategies on the situation. So the simulation of program must schedule the events in the simulation, so the activities will occur in the correct time sequence. For instance, suppose a person visit an outlet at time t1 to deposit its cell phone bill. The transaction may be expected to take time t2 to complete. So in any of the service window, if it is free, the person can immediately deposit the bill in t1 plus t2 times, spending exactly the time required to deposit the bill. So if none of the service window is free, there is a queue waiting at each window. So the person joins the smallest queue and waits until all the previous people deposit their bill and he leaves the line. In this case, the time spent by the person in the bill will be t2 plus the time spent in the waiting queue. So such problems are solved by writing a program to simulate the actions of the person. So the various service window, they are requested by different represented by different queues, and each person waiting in that line is represented by a node in that queue. So the node at the front of the queue represents the person currently being serviced at the window. So we can define various events associated with the process, like arrival of the person, departure of a person. So when a departure node is removed from the event list, the amount of time spent by the departing person is computed, and it is added to the total and the node representing the person which is removed from the forefront of the queue. So after a node has been deleted from the front of the queue, the next person in the queue becomes the first to be serviced by the window, and the departure node is added to the event list. So at the end of simulation, when the event list is empty, the total will be divided by the number of person to get the average time spent by the person. So these are a few more questions on the data structure algorithm, and I would advise you to really see the government book or the famous books which are available, so that I'm just giving you an idea. The exact study will be only when you really look to the book and understand it very carefully. Thank you so much, and this my discussion will really help you. Thank you so much.